Hi, I'm Ben-Yaakov. This presentation is entitled Ferrite Beads in Power Electronics. There are a variety of beads, of ferrite beads available. They are this SMT type to put on a PCB. Here is the structure, and inside is wires, and actually it's embedded or casted into a ferrite material. And then we have this cylinder type in which the wire is going through it. And of course we have the clamp on, which are put on a cable. So what's the purpose of these beads, of these ferrite beads? I'm showing here two examples. One is the case of a power line. Here we have a converter, a switch mode converter by analog devices. This is the actual output, but in order to further attenuate the noise, EMI, interference, you can put a bead here. There is a capacitor which is sort of forming a filter, and by this we are going to get a cleaner signal, or in this case it's a DC coming out of this converter. Another example suggested by a company that makes gallium nitrate transistors. These are GaN transistors, transform, and here they suggest to put a bead in the line in between the driver and the gate in order to attenuate possible oscillations in this line, which could of course harm the unit by turning it on and off at high frequency. So these are just two examples of filtering of EMI, either in a power line or a signal line. This is actually a sort of semi-power line because the current peaks are high here. Now there is a common misconception thinking that the bead acts like a filter, like an L, like an inductor. So you have like a one turn, there's a ferrite, so it's like an inductor. This is wrong, this conception, because in fact this is something you don't want. Because if you have an inductor, especially in a switch mode power supply, the losses are low in the system, and consequently the Q, the quality factor of this resonant network, is bound to be high. And consequently, when you have say a step which has all the high frequency components, it'll start oscillating, and here we have interference actually generated by this thing. Of course it's a filter, but around the resonant circuit it's bad news. So the bead is not supposed to work in this way. In fact, in the bead you'd like to have the damping effect, that is the resistive, the lossy effect. So the operation of a bead is absorbing the interference rather than attenuating it. In other words, the bead is supposed to actually convert the interference into heat by absorbing this energy. So it's a different story than a regular filter. So let's have a look at the material which are used to build these ferrite beads. Now this is a typical data sheet characteristic of such a material. This is a 43 material from ferrite. This is again an example. There are many companies making these beads and the materials, so there's no recommendation or endorsement here, just an example. And the point is that we have here, it's kind of interesting, this is the permeability here, this is the frequency, and we have now two permeabilities. One is the real one, it's a mu prime, and here it is. And then we have the so-called complex one, which is, here it is, and mu double prime. Now, the inductance of an inductor built with this material will be something like a constant times mu, which is frequency dependent, here this dependence, and the complex component, mu of double prime, J times and a minus here. So this is the general representation of an inductor built with this material. Now the impedance, of course, is J omega times this inductor, which is frequency dependent. These two are frequency dependent. And therefore, when you multiply it, you'll get this component, which is sort of like an inductor, although it's a frequency dependent inductor. But you'll get here another component, which is a real one. So this is a resistor. The impedance here, this is resistive part. And this is what you want, in fact. This is something that you get for free, and this gift is not very welcome. So this is what you want. So the total impedance of such an element will be the inductive part plus an RAC part. This resistor is kind of strange. It's a frequency dependent, so a DC, there's no resistance, and it's depending on the frequency, and it's depending on this mu. This is the higher the mu, the higher will be this value. So typically, the manufacturer will give us this type of information. Here we have the impedance of an element. This is a specific element now, specific bead. This is a frequency. It goes up to, this is 1 gigahertz, 10 gigahertz in fact. This is 1 gigahertz. And this is a TDK example. Again, there are many companies who are making it. What we see here, actually 3 curves, which are the key data that we need. One is the inductive part. Here it is. This is the inductive part. This is omega times L. L is frequency dependent. And what we see here, and this is due to this mu, of course, and times frequency, that it goes up and then actually it goes down because mu is dropping at high frequency. Now, the resistive part is again going up with frequency dependent, and this is a very important crossover in which the resistive part is larger than this inductive part. Now, the sum of these, of course, it has to be in a phasoric way because there is a 90-degree phase shift between these. The sum here is this total impedance, which is this outer curve here, which is the sum of these two. This is the total impedance that you have of this element. So, as I've said, this is the important part. This is the crossover between the inductive part and the resistive part. So the equivalent circuit of a ferrite bead would look something like this. We have the inductive part, we have the resistive part, and there is the RDC. This is the wire itself. It might have also an AC component to it due to perhaps skin effect, but let's leave it as a RDC, the resistance of the wire. There's another way to represent the equivalent circuit, and this is by parallel components, and plus, of course, the RDC. Now, this is really not physically based. You can sort of trim these values to behave like this one. In fact, there are companies like TDK who give you, they call it a simple model, and these are these value, and here are, these are actually now fixed value, so that over the frequency, the impedance here will behave somewhat like the original impedance. I think this is not a very good representation. I think there's a problem with the phase here. So I think the best way is actually this way. But notice that this is an RAC, so if there is a DC through this element, this should not be taken into account. So it's a kind of a funny type model that is for AC. It's not for DC, because in DC this element is not there. So companies are making material for different frequency ranges. For example, TDK shows here that there is a B material which is applicable for the low frequency region, and then there's this D material which is applicable to frequencies approaching the gigahertz and hundreds of megahertz. So for each particular application, you can actually choose the material that will be most proper for the frequency range that you are working at. Now, there are problems here. One of them is the fact that DC current will shift the permeability, because the permeability is the slope here of this hysteresis curve. This is a ferrous cube material, and you see that the permeability, which is the slope here, is changing. Here it's high and it's low. So therefore, as the current, of course, which is generating the magnetic field, is increasing, when the current is increasing, mu is going down, inductance is going down. So if you start with zero current, and this will be this curve, this for a TDK unit, a ferrite bead, then as the current goes up, for the given frequency, the inductance or the impedance will go down because the mu is actually changing. So this is one problem that has to be taken into account. Another one is temperature dependence. These materials are also temperature dependent. You can see it here. In fact, this is the hysteresis curve for 25 degrees, and this is for 100 degrees. So it's quite a bit of a difference between these two. Another product is the clamp-on, which is, from the physical point of view, from the ferromagnetic point of view, the same thing, except that the structure is different, and you just clamp it on the cable. And here again, we see this is for this particular material for Ferrite company. We have here the XL, we have here the resistive part, and then this is the total impedance, which is the phasoric sum of these two. Now in case you have more than just one turn, when you wrap it around, then of course the inductance will go up as n square. So if you have one wire just going through, you have a certain value, and then if you have 3 turns, sort of, it'll be like times 9, and 5 turns, it'll be like times 25. So this is like any other inductor, dependent on the number of turns. So what is really the purpose of the clamp-on ferrite? This is a rather complex issue, and I cannot go into all the details in this short video. Let me just give a short and sort of introduction to the subject. Here we have a typical situation. I have a power supply, that's a buck switch mode power supply, and I like to measure the output voltage, let's say the ripple at the output. Okay, now let's even assume that I have a differential probe or have a scope which has a differential input. It's the best situation possible. So I'm connecting these two to the output, but as it turns out, between any two systems or any two cards or PCB cards, you will have a difference in the potential between the two grounds. There's no escape from that. So if we look at the possible current paths, we're going to have here through this source or this potential difference, we have a current going here into the two wires. It's a common mode current into this part. And then I'm showing here two capacitors, but these are in general, of course, impedances, and the current is going through these impedances. Now, if these are not equal, and they'll never be equal, you generate a differential voltage. Once you have a differential voltage, then of course you're going to see it here. So superimposed on what you measure, you see this noise which is coming through this different potential between the two grounds. So now we're going to put a clamp, a ferrite element on the two wires. Now for the current, for the signal itself going back and forth, these currents are canceling each other, so there's no effect on this differential current. But for the common mode current, there is a higher impedance now, depending on the core, depending on the material, etc. And therefore, it'll sort of introduce a high impedance for this common mode current, and by this it will attenuate the current, and therefore the differential voltage will be lower. So this is the idea of putting a ferrite on a cable rather than on a line. Now, this is not without any problems. For example, if I have a coaxial cable, here it is, like a probe, a scope probe, then I have interference in the area coming from this source or other sources, and then always be a capacitive coupling to this large area of this coaxial shield, and therefore there will be coupling here to one wire, and as you can see, this now becomes a differential current. So this will not help very much for this type of interference, and there's something else you have to do. So it's not a magical solution to everything, but for the common mode, it can really help. So let's go now to the very fine details here, although it's a short video and it's an introduction, so I cannot go into very many subjects here, but still let's just understand what are the problems here and how do we cope with them. So the first thing is to realize that if you are not choosing the bead properly, the ferrite bead properly, it can actually do more harm than it is actually helpful. This is very important to realize. I mean, it's not a magic thing just to put the bead and that's it. In fact, you can put the bead and the situation will be worse. We'll see it in a minute. And then the point that you have to worry about is this inductive part, because this inductive part with capacitive, either parasitic or capacitors that you have in the system, may cause oscillation and interferences, and this could be bad news. So the crossover frequency, this is the key factor here in the selection of these elements. And there's no escape at this point, since we don't have good models, we don't have good analytical way to analyze this system. It's a trial and error approach. That is, you try a bead, select it, test it, and then if it doesn't work right, you just choose another one. So there's no really a straightforward one way to design the system with a bead. And here are some examples. This is actually an example from TDK, and this is a TDK element. And what we see here is the following. If I have a system like this is a signal line, and I'm putting beads, options to put a bead here, here, or here. It turns out that it doesn't make much of a difference, but in this test they've tried 3 positions here, and this is the signal itself. I don't know if you can see it in the video, but here there is a sort of spike, small spike, that's overshoot and undershoot high frequency spikes here. So this is the original signal. And if you don't do anything, this is what you get just about at the output. Now, you can put a bead, here it is, and this bead is really improving it. You see that you don't see this spike, it's sort of making it a low frequency rather than high frequency. There's no high frequency component here. And there's a sort of a slight difference. You see that in fact, if you put a bead here, it doesn't help much because it's this line is now reacting. In fact, since this is generated, the source itself has the spike, then you better put it at the source, if the source is the reason for the interference. If the line is the reason for interference, then of course you need the bead here. Now, at the bottom, what you see is also a bead, a ferrite bead that was put in this line, same position. It's a different bead, they're not saying which one. And you see it's getting worse. It's much, much worse. And the reason is that there is a inductive element or inductive part here, which is reacting with the input capacitance of this gate and sort of oscillating. It's sort of damped down, but still the oscillations are very high. So here's the bead, and here is the bead, and you see that here it's helping, and here it's just making it worse. Here's another example. It's also by TDK, in fact. we have two cases. These are two beads. Here, there is a crossover point at 12 megahertz. That's here, between the inductive and resistive part. And here we have it at 5 megahertz. So now we have a pulse. And again, I don't know if you can see it clearly. This is an undershoot, a very sharp undershoot here. And then they put this bead and this bead in the line. They don't show exactly the circuit, but really doesn't matter to make the point. And what we see is the following. This bead, which has a higher crossover frequency at 12 megahertz, is actually making the situation worse. The spike is actually getting bigger and wider, and this is much worse than the original one. On the other hand, if the resistive part is dominant at the frequency of interest, this is the frequency content of the spike, then this spike is sort of attenuated quite a bit. There's a little wiggle here, but there's no spike. So this one is really helping. This one is making it worse. This is frustrating, but that's the situation. Now another example we have here. This is by analog devices. This is again this power supply or switch mode converter, and then we have the bead, and then we have a filter here, filter capacitor. By the way, this is shown for really rather low current, because you see 3.2 kilo ohms, so the current here is, the load is low. Now, there are three situations here. One is that there is a bead and a capacitor. That's it. That's the normal case, let's say. And then there's a case in which they have added a resistor instead of the capacitor for damping. Okay, damping what? Damping this resonant circuit that might cause oscillations here. So this is method A with a resistor. Method B is a capacitor plus a resistor across the ferrite, again for damping. And method C is again the bead capacitor, but then we have like a snubber here, where the idea is that for the DC, this is actually blocking the DC, and now you can put a small resistor that will absorb the AC without harming the DC or without dissipating DC power. So this is like a snubber, and these are the three situations. And here are the frequency responses of these filters in the three situations. For the undamped, the regular one, that is the bead plus the capacitor itself, nothing else, this is what we get. This is very bad, because here we have a very high gain, and therefore if you have a sort of a step, you're bound to have a frequency in this region, and therefore you have an oscillation. And of course it depends on the bead. You could have chosen a bead which will have a less of a hump here, and this is the whole story, that different beads behave differently. Now, for method A, this is method A, we see an improvement. Here it is. Method B, we see an improvement in terms of the attenuation, but here it's still, there's a peaking here. And method C, with this snubber-like damping, is actually the best. So here they are showing the actually spectrum of the signal in this case. And we see the original is the dark one. We see high components here. And the orange one here is the regular bead plus capacitor. That's it, no damping. And we see that, of course, there's attenuation at high frequency, very nicely. But in fact, at this point, this is 2.5 megahertz, it's worse. Why is that? Because at 2.5 megahertz, we got this thing here. As it turns out, the system itself has a peak at 2.5 megahertz, which is now being amplified, you might say, by this resonant circuit, making it much worse. Now, in this case, again, the dark one is the original, and this one is method C. Method C is the snubber light, okay? This is the method C. And what we see here, that of course it's improving here as before, and since there is no peaking, there is attenuation, a slight, well, it's not very high, the attenuation, there is a slight attenuation in 2.5 megahertz area here. So we can see that the situation is really complex, that you have to worry about possible reaction of the inductive part of the bead with the capacitances that you have in the system. And here I'm going to show some simulation that I've made with a model that I've developed. And this model actually reproduces the behavior of a bead. So first of all, this is a synthetic. It's not a specific bead. It's just something that I've sort of built myself, although I could have fitted it to any beads available. So what we see here again is this is the impedance, total impedance, this is the reactive part, this is the inductive part, and this is the resistive part, and the impedance, of course, is the phasoric sum of them. So I'm going to test this simple filter. This is the source, and here we have the bead, which has this characteristic. We see that the impedance goes up to, say, 500 ohms. So this is 50 ohms, so we're going to have an attenuation when this is at this frequency. And of course, at higher frequency, this parasitic or filter capacitor, you might say, will attenuate it further. So here it is. We see that indeed there is an attenuation due to the impedance developing here. Here it is. And then, of course, the capacitor is attenuating further the signal, so the V out to V in is of this nature. Okay? So we see that the bead is actually doing its work and attenuating the high frequency signal. Now let's have a look what happens when I have a time domain case. That I'm looking at the signal in the time domain, not just the frequency domain, not like the AC analysis. And here, what I did, I've put here a sort of a square wave, a main signal, plus sort of noise, very high frequency noise. And as you can see, these noise at the input, which is here, is fairly high, okay? It's a 1 volt pulses, sharp pulses. And as you can see, as it goes through the filter, it is really attenuated considerable. So this shows the power of a ferrite to indeed attenuate the high frequency component and make this picture very, very clean. Now, however, as I've already said, the situation is not cut clear. I mean, there are many variables here. For example, if you change the load, here it is, I've enlarged it to 220 ohms, and this is now 330 picofarad. And what I got here now is some overshoots and oscillations, because now the reactive part, the inductive part here, this part here, is now reacting with this capacitor and generating a oscillation at a frequency which is in this region, and therefore the attenuation is not that good, and we see here this overshoot and this undershoot. So as you can see, there's a lot of information here, and unfortunately there aren't many tools that you can use in order to sort of foresee what's going on, and there's a lot of trial and error involved. And of course, if you do have a SPICE simulation model, then it could help, as it can accelerate this trial and error procedure. So this brings me to the end of this presentation. I hope you found it interesting and perhaps it'll be useful to you in the future. Thank you very much.